Hello and welcome to the first of the EGM37 Additive Manufacturing e-lecture. This is e-lecture 1, and it's just a refresher on some of the manufacturing processes and just putting the manufacturing processes that we're going to talk about throughout this in some sort of context where we compare them to additive manufacturing. So, well, the contents of this, just a reminder, is this refresher on the manufacturing process. We're going to talk about different types of processes, the material, how they can classify them according to the material phases, which change as the process undergoes. We talk about subtractive processes, additive processes, continuous processes, and net shape processes. And after every lecture that we have on Blackboard, the plan is for you to go ahead and do a quiz test on Blackboard just to track your knowledge of the lectures and to see what needs to be done. So we can classify manufacturing processes, a general classification through subtractive manufacturing, our additive manufacturing, which is what we're going to look at in detail here, continuous processes, and net shape processes. So these we have generally defined as subtractive manufacturing as a process involving the controlled removal of material. Additive manufacturing defines itself on the process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodologies. Continuous processes, those which fall into the category of theoretically producing indefinitely long material, for example, like extrusion, continuous extrusion. And then net shape, which tend to be batch-based, where we create an object in its finished form without the need for finishing or other actions. On the basis of the classifications, there are other ones. We can look at the geometrical transformation itself, so whether it's subtractive, additive, and net shape, so it changes the volume somehow, although there's geometrical shape. We can base it on the time, whether it works in serial or it can work in parallel. And then we can also base the classification on an energy domain. So therefore we can have mechanical transformations, thermal, furnace-based, chemical, electrical, and so on. There's more. If we look at the part mass, just a general sketch to show different types of the additive, you can see you have a constant increase of the mass as you add the layers. Net shape tend to be just a one-off, like a casting, and they don't necessarily change the mass per se of the part. But with the subtractive, we start with a block, and we can either work in serial or parallel to reduce the mass of that block until we get the component that we want. So if we were looking at classifying manufacturing processes through the material phases which are formed, we might have a solid phase only, where, for example, machining, bending, forging, we're not necessarily changing the phase. Liquid phase, we may melt the material and cast it or mold it. We could have a mixed phase with composites, where you could have solids which are impregnated with a liquid form, which would then go solid. And we can have vapor phase, like chemical vapor deposition or physical vapor deposition, where we're actually working with a gaseous form of the metal, which is deposited on the surfaces. Just to go through some of the pros and cons of the different processes, if we start with subtractive processes, we can have processes like machining, turning, milling, boring, grinding, and the non-traditional forms of these, more like electric discharge machining, chemical milling, and mortar jet, which are more. And then these are also processes where we're in microelectronic processes, where we have sort of etching, where sort of different surfaces get etched at different rates with masks or a beam, and we can have chemical milling, chemical mechanical polishing. Now there are pros and cons. Most of these are very generalized pros and cons. Material properties are relatively independent of the process because we're not changing the phase of the material. The material properties that we start with are the material properties that we end up with. So if you were to machine back a block of TI64 and take it down to a particular component, that component will have the same or very similar material properties as the original block of TI64. It's flexible. We tend to have very good dimensional control, so we can get down to very, very good geometrical tolerances. and generally the surface finish is good. Now, on the con side of the negative side of this, it's a serial process, so they can take a long time. There's sometimes a lot of operator. There's one of the main criticisms on the subtractive processes is a large amount of waste. Sometimes to get the properties that you want, you would take in that level of waste to guarantee the mechanical properties of the material. So again, coming back to the example of a block of Ti64, you could have as much as a waste of 20 times. So you have 1 kilo of component will have needed to be machined down from 20 kilos. And this is, for example, with the manufacturing of the aircraft components, such as door frames, which need to come down from very large ingots. So there's a large amount of waste, and often that waste can only be downgraded. Now, examples of subtractive processes here, some images. So there's milling and lathing. We've got slab milling, face milling, and end milling. We've got an example of a water jet there. And what we're going to have a look at now is an example of electron discharge machining, which, if you're interested, there is in the workshop here at Swansea. We have an EGM machine. And now let's see if this works.
Making parts with highly detailed, extraordinarily tough shapes and tight tolerances can be nearly impossible with conventional machining techniques, but not with a wire EDM process. Imagine being able to make precise cuts in metal with a blade no thicker than a human hair. That's what wire EDM can do. EDM stands for electrical discharge machining. But instead of a blade like a bandsaw, wire EDM uses an electrically charged hair-thin wire to remove microscopic particles and shape the part. These animations help show how wire EDM works. The wire carries one side of the charge, conductive material carries the other side of the charge. And when the two get close, a white-hot electrical spark jumps the gap, melting away tiny dust particle-sized pieces of metal, 2 microns or smaller. How small is a micron? Well, if this was the diameter of a human hair, this would be a micron. But what's all this liquid? Well, that's the dielectric. Deionized water, really, useful because it doesn't conduct electricity. In wire EDM, the liquid dielectric controls the sparking, cools the process, and flushes away those tiny particles as they're removed. All very fast, about 1 million sparks per second. The particles themselves are each about the size of a particle of smoke. In the right hands, wire EDM can be used to hold really tight tolerances, create incredibly complex shapes, work with difficult materials that may be extremely hard or soft, and if needed, make really small parts. There's even something called small hole EDM for working from the inside of the hole to the outside. All completely automated and CNC controlled. No human involvement. At Exact, wire EDM is all we do. We're very good at it, making us the perfect wire EDM partner to produce complex precision parts that all.
Anyway, I showed you that because EDM is of interest often to us when we're making additive parts, use metal parts, just to take things off the plate more than anything, but also to finish them. So now we can look at some of the comparison of the removal rates of different subtractive processes and the energy levels. So material removal rate is in the volumetric rate of millimeters cubed per second, and you can see the energy consumption as the material removal rate goes up, which basically means that the efficiency is improving even though the power demand goes up. The rates will change through different processes, so we'll have higher rates of removal, for example, here with some types of machining, rough machining, obviously. Laser is somewhere in the middle, so laser etching, laser removal. EDM, relatively on the low rates of material removal rates there. So we're going to use some of this as a way of comparing. Not that we always have all parts can be made the same. So not necessarily you can make all additive parts by machining, but some parts can be machined and additively manufactured. So therefore, it's good for us to know that what we can expect in terms of power usage and work out to work out the techno-economic cost of the process to be able to compare the two together. So power demand and energy estimates for machining operations. So we have power in watts equals a baseline power plus a specific energy times material removal rate. Okay, the specific energy is given in watt seconds per cubic millimeter. The material removal rate, as I've said already, is given in volume per second, millimeters cubed per second, and energy can then be estimated from the power times the time that it takes to make a part. Looking at through the table here, different approximate energy requirements for different materials. You've got aluminium alloys there with the specific energy ranging between 0.4 and 1.1. And here we've got it in both SI units and imperial units. So cast irons there with a higher specific energy of 1.6 to 5.5, copper alloys 1.4 to 3.3, and so on. So specific energy, as you can see there already, is a function of the hardness of the material. So you can see here that the harder the material, obviously, the harder it is to machine, and the lower the material removal rates which are achievable. So you've got, for example, on the left-hand side here, you've got titanium and cast iron. Cast iron can be incredibly hard. And then you've got steel with a wide range and aluminium with a relatively wide range, depending on what specific alloys, steels, and aluminium we're looking at. So we're going to go ahead and use some of these things just to do a quick calculation here. So, as an example, to look at the energy consumption of milling a steel block, in this case 316. Stainless steel, let's say we have a 250 millimeter long plate, which is 250 millimeter wide, 50 millimeters thick, and this is then milled using a CNC milling machine. Okay, and we're given that the specific power requirement for this metal is 3.7 watt seconds per cubic millimeter, and the material removal rate is 2 centimeters cubed per second. So what is the cutting power required and the energy used to mill to a depth of 5 millimeters? Yeah, let's assume 80% cutting efficiency. So with all of these calculations that you'll see from now onwards, they're relatively simple putting together. What we have to make sure is that we work in the same units. Okay, so we can see already that we're given something in centimeters cubed per second, and here we've got millimeters cubed. So first of all, let's work out what the volume of materials moves is. From that 15 mil thick plate, we're going to take it down by 5 mil. So the amount of volume of material that we take out is 250 by 250 by 5 millimeters cubed. That's 312,500 millimeters cubed, which is also the same as 312.5 centimeters cubed. Now the material removal rate is 2 centimeters cubed per second, or 2,000 millimeters cubed per second, and our specific power requirement is that the metal, for this particular metal, steel, is 3.7 watt second per cubic millimeter. Let's ignore the idle power because we don't know enough about the machine for now. So the cutting power, P, is just K times MRR, or the specific power times the material removal rate. So we've already worked out that the MRR is 2,000 millimeters cubed per second, and the specific power is 3.7 watt second per millimeter cubed, which gives us 7.4 kilowatts. So the duration of the milling can be worked out to be the volume of material removed divided by the MRR, which is 312,500 millimeters cubed, divided by 2,000, so roughly estimated 156.25 seconds. Okay, so just over 2.5 minutes. Energy is time times power, so if we take that time, 156.25 times the power, which we worked out was 7.4 kilowatts, or 7,400 watts, we get joules. So our energy is 1,156,250 joules, yeah, divided by 3,600,000 to get kilowatt hours, gives us 0.32 kilowatt hours. So the actual energy is the energy divided by the efficiency. So we say 80% efficiency is 0.8, so our actual energy is 0.4 kilowatt hours. Okay, let's continue on this vein of working out the energy consumption in machining different materials. So we have here a cylindrical shaft for an air engine component is machined from a titanium billet of Ti6Al4V alloy, which is a titanium alloy. The original billet has a 0.7 meter diameter and a 0.5 meter height, and the final cylinder has to have a 15 millimeter wall thickness. You can see the final part is just a cylinder. Okay, and it has a 15 millimeter wall thickness and an outer diameter of 0.66 meters and a height of 0.5 meters. So two questions. What is the buy to fly ratio? And then the second part of this is, given that the MRR is 10 millimeters cubed per second, material removal rate is 10 millimeters cubed per second, and the specific cutting energy is 3.7 watts second per cubic millimeter, what is the total electrical energy required to produce the part? Okay, so let's start with the first one. The buy to fly ratio here is the ratio of the volume required to produce the volume of the part. Okay, so in essence, it's an estimate of the amount of material that we've wasted. And buy to fly comes from the obvious connotations with aerospace. So let's work out the volumes that we need. Outer diameter 1, 700, outer diameter 2, 660 millimeters, inner diameter 2, 630 millimeters, height 500 millimeters. So we can just use simple calculations of cylinders. Get the first volume is 192,422,550 millimeters cubed, and the second volume is 15,197,454 millimeters cubed, and that gives us a buy to fly ratio comparing the two volumes of 13:1. So we worked out here the amount of volume material that needs to be removed is 177,225. Okay, sorry, back again. Yeah, so if we take volume 1 from volume 2, that gives us the material removed is 177,225,195 cubic millimeters. Now we're given that the material removal rate is 13 cubic millimeters per second, and the specific energy K is 3.7 joules per cubic millimeters. Okay, so the power is K times MRR, which is 48.1 joules per second, or watt. And therefore, the material removed divided by the material removal rate is 13,632,699 seconds. So therefore, the energy is time times power, both in watts, seconds, which is 655,732,853 joules. So therefore, the energy is 182.15 kilowatt hours. Now, additive processes. Moving on to our next type of processes. Additive layer manufacturing, rapid prototyping, 3D printing, wire arc manufacturing. We're going to hear a lot about these throughout the rest of the course. But other types of additive processes are composite processes, laying composites, epoxy, carbon fiber. You can have microelectronic processes where vapor deposition is put down one layer at a time using chemical vapor deposition. But joining an assembly, so welding, adhesives, and mechanical processes, these are also known are also additive processes, but not necessarily powder bed or the type of additive process for 3D printing. Pros and cons. So additive processes give us a chance because we're laying them. We can have tailored materials. We can often, with some of them, create some incredibly complex three-dimensional parts, so structural complexity, and also give us a level of automation. Now, mostly the processes are slow and sequential, batch-based. For some of these, not all of them, there's quite a high level of waste. And the materials that come out, particularly for composites, are often hard to recycle. So we'll look at some of these examples. The advanced composites, filament winding. There's a filament winding machine laying up there. With microelectronics, here's another process. Here, a wafer being produced in a furnace. But we're going to talk more about additive processes, a lot about additive processes and what's coming up in the next chapters. Now we're going to talk a little bit about continuous processes. So these are processes like metal extrusion, so you're pushing material through, or plastic extrusion, or continuous casting. We can pull material through dies, and the protrusion of composites and crystal pulling and the string ribbon process. So continuous processes give us a way of producing a very low cost, unit cost for materials. So a lot of them are materials are used in construction industry, often extruded, but we have relatively simple cross sections, relatively simple. Sometimes they can be complex, but they are always they have a constant cross section as it's being pushed through the die. So there's a limited amount of complex generation. Here are some examples. We used to have an all metal extruder here on the right, which is why I put it in there. And here's composite protrusion going through, and that's the process. If you want to find out more about that, another process. Net shape processes. So really, of all the processes, I've really picked out a little more to talk about here. A process whereby we have an element of comparison is used with additive, 3D additive processes. So we might have this different types here of processes like dealing with solids, so metal forming. It can deal with powders. It might deal with liquids such as casting, injection molding, lots of different types of casting, as you probably know. You can have investment casting, sand casting. You might have mixtures. You might infiltrate. You could potentially have a liquid metal infiltration process, whereby you would have a powder metal and you might infiltrate it with a brazing alloy. So, and it produces all types of different types of characteristics. You can hard tooling, solid forming. You can have quite a fast time cycle, so things like high pressure die casting, thermal processes, so slower dependent on the cooling rate. Dimensional control is not as good as machining, but it can be quite accurate. So we have fast cycle times, and we can deal with large volumes. These are pros of typically net shape processes. Most net shape processes, particularly casting type processes, where it's associated with a low cost. Cons: sometimes on the negative side, things like high pressure die casting or die casting generally, you need to have a very hard tooling. You need to often have cooling within the tooling. Because you're going through a liquid phase with some of these, or powder-based methods where semi-sintering, and you end up with porosity. So sometimes the material properties associated with the material that you're making are not necessarily as good as they might be done through other processes. Sometimes achieving net shape can be very difficult, particularly for thin sections. And because you use molds and dies to trap to form the shape, you can often get contamination of the alloy. So reactive alloys like titaniums and aluminiums can often get contaminated with the mold that you're using. And over time, with processes like investment or injection molding, you also get wear of dies which have to be replaced, and these can often be very expensive to prepare. So here are some examples of net shape processes. These are dealing with powders, so powder compaction, where there is a tool which punches powder maybe from two different directions, and as you can see, it consolidates the powder and takes it through, but you still end up with some level of porosity which requires this to be either heat treated or hipped. So HIP is hot isostatic pressing, where you can actually have form by using hot isostatic pressing, which is also a heat treatment for some materials, but in this case we're using it to take powders, which is put into a case. The case has got a shape. Okay, it's vacuumed out and crimped, and then the shape is formed within. This is actually called a can. Okay, the can is deformed under high pressure and high temperature, and then the can is removed to give you so the part underneath may be removed by either chemical milling or machining, or by chemically milling back to the part shape. So it's a semi-net shape, near net shape, really, more than anything, because you still have to take off the cam and do finishing operations on the component. So if you're interested in looking a bit more about powder compaction, here are some papers, actually one from Swansea. This shows you quite nicely the stages of the consolidation of titanium 64 powders and the powder compaction. And you can see how there is sort of plastic deformation happening at different points of contact between the powders. Here's a simulation of something very similar using finite element by Professor Gethin and Professor Ansing here at Swansea. We couldn't move through net shape processes without talking a little bit about investment casting and die casting, which I already mentioned. So investment casting, these are very old processes, been around for a couple of thousand years and have improved in that time. But they're very complicated processes with many steps. We have to have a wax pattern, which is then dipped to create it's formed into a tree with the components on them. It's dipped into a slurry, which is then coats it, and then you pour the molten metal into the pattern, and you get yourself the parts, which then have to be removed off the tree. Setting this up is complicated, and it is prone to many failures as you get to get it right. Die casting, this is the relatively slow process. Investment casting is relatively slow. A much faster form of casting is the die casting, where you actually pour molten metal into a potentially copper mold, which is cooled, and this can be, or aluminium, and this can be done cycled very quickly to produce small parts. Sand casting, you will have this is quite craftsmanlike, but even some high interesting aerospace alloys will get done by sand casting, and you'll have a cope and drag, which is called the top part and the lower part, and you'll have green sand, which is fashioned out very similar to a certain extent to investment casting. You have the shape, you basically form an internal cavity through which you pour metal into the basin or funnel, and it comes down these sprues, and then it rises up through the riser, and this part here is the component which is then taken out, and you need to remove the additional metal. Yields anywhere here between 40 and 60% means that there is quite a lot of material that needs to be reverted. Other net shape processes I'm not going to go into too much detail about were forging, stamping, smaller parts. All of these processes have very different cooling rates, and we're going to come back to this later on when we look into the physics of some of the additive manufacturing processes. We can see cooling rates, quite low cooling rates here, typically associated with casting, but quite a range. Additive manufacturing, it also is somewhere in the middle range of cooling rates, and what we've done is we scaled it by the size of the components that can be made. So casting, obviously, sort of 0.5 meter to 1 meter, but we can go much higher than that. Additive will be quite small parts. Then we have the heating rates associated with some of these fast cooling, like gas atomization here, which makes very cool small particles, but they get cooled quite rapidly as they come down in the hoppers. And we've got electron beam welding, laser beam welding, and rapid solidification with very high cooling rates. And all these different processes require different levels of energy, so we can kind of look at this in the efficiency, electricity requirements of the different processes. And we might have some of the sort of more machining elements down here with relatively higher process rates but low electricity requirements, and then you've got whole scale going down and lower process rates and low amounts of volume of material being produced by the process. So let's pick out another one here, chemical vapor deposition here in the middle. Relatively low process rates, but quite a lot of high energy requirements there. We can see the EDM, drilling EDM, is actually removing very little material for a very high amount of electricity. Anyway, so that completes this e-lecture number 1. Now it's worth going to see if you can have a go on Blackboard at a few questions on this test.